Hello, everyone. My name is Malvina and today I will be presenting a joint work with Federico Ciccozzi, Mattias, Mohlin, and Ernesto Posse titled Towards Automated Support for Blended Modeling of UML-RT Embedded Software Architectures. So to begin with, software steers our daily life, and methods for more efficient and effective architecting have been a focal point of research for years now. Two main ingredients of efficient architecture are automation that boosts the throughput and improves the quality of results, and abstraction in terms of modeling that allow it to focus on the problem from a more human-oriented perspective. Now, these two are also considered as a core pillar of model-driven engineering, where models are first-class entities and they help you abstract from certain aspects of the problem at hand. The abstractions that are domain-specific are described in domain-specific modeling language. Moreover, there are also generic purpose languages such as UML that allow to describe domain-specific concepts through UML profiles. Now, of course, in order to model, we need modeling tools. But the modeling tools either support graphical notations, textual notations, or both of them, but in a mutually exclusive manner, meaning that you can either use one or the other, but not both. However, this limits human communication, limits the pool of available tools that are needed, and negatively affects the throughput. So a solution to that is blended modeling, which is considered the activity of interacting seamlessly with a single model through multiple notations, allowing a certain degree of temporary inconsistencies. So it is really important for a blended modeling environment to support at least graphical and textual notations in parallel, and also manner synchronization in order to ensure consistency. That will lead to faster modeling activities, flexible separation of concerns, and better communication. So in this work, our focus is on a modeling tool for UML-RT architectures and applications called Rtist that only supports graphical modeling. It models structures through composite diagrams and behavior through state machine diagrams. Moreover, it uses C and C++ action code for the description of algorithmic behaviors within graphical state machines. Now, even though the latter is itself textual, it is a foreign entity that has no overlapping with the graphical model elements. So in Rtist, what we have are graphical notations in order to model architecture and software. In this work, we narrow our focus only to the behavioral part, meaning state machines, and our contribution consists in what we need to turn Rtist into a blended modeling environment. The first step into doing that is defining a textual notation, and the second step is integrating the textual notation in Rtist so that we can later provide synchronization mechanisms that will ensure consistency between the two notations. But we have to make sure that these two notations should be at least partially overlapping. So let's begin with the approach on defining the textual notation. The chosen framework for that purpose is text, and we can either do that in an automatic or manual manner. We decided to define the grammar manually because the one that is generated automatically is erroneous and unintuitive. While if we define that manually, we can do it according to the expectation of the Rtist customers and architects. So the steps that we followed to manually define the grammar were to first identify the reserved keywords so we could typify the core concepts of the language, to define their ordering strategy for enhanced readability and navigation, and to add a spoonful of synthetic sugar so that we can make the grammar more compact and support the joint use with the C++ section code. Next step is to try to integrate this grammar in Rtist. That is achieved by customizing the Xtext AST factory and linker. Now, the Xtext parser creates the state machine abstract syntax tree, and that needs to be inserted into the proper model context, which in our case is the capsule to which it belongs. When this is achieved, then Rtist will treat the state machine that is modeled using the textual notation the same way as it does for the one that is modeled using the graphical notation, because the model representation is identical. So while integrating the textual notation in Rtist, we identified some challenges involved in synchronizing changes across the graphical and textual models. So first are the incoming cross-references. Now, one can create dependencies from the capsule to a state in the state machine. However, if one decides to delete the state machine and insert a new version, that could break cross-references since the deletion will trigger cleanup of cross-references. So measures should be taken that updates should not happen through deletion and insertion. Second is that we might lose model information that is available in the graphical model, but not in the textual one. And if we update the state machine due to a change in the textual notation, what happens is that the AST created by the graphical notation together with the additional information is deleted, and that the AST created by the textual notation is inserted. The solution in this case would be to merge these two ASTs so that we can still keep that information and not lose it. A third challenge is to ensure the stability of the URIs of elements. Now, every time the state machine is modified, elements get new URIs, and incoming cross-references cannot be kept bound. So the solution is to implement an Xtext fragmenter that uses fully qualified names instead. Last challenge has to do with code formatting and comments. Now, the lexical entities carried by the textual notation are not reflected in the AST. So if the state machine is modified to the graphical editor, those changes will be lost. So we need to find semi-automated solutions in order to preserve code formatting and comments. So to summarize, the definition of the textual notation and its integration in Rtist are the first step towards a fully blended modeling environment. We had satisfactory results achieved via the textual notation from the involved architecture at HCL, but we intend to extend the textual notation to the rest of UML-RT concepts and to run extensive controlled experiments and industrial case studies. Moreover, we intend to implement this approach using other graphical modeling tools and compare these results. Last but not least, we envision a web-based modeling solution by leveraging the language server protocol, and in particular, the graphical LSP in Eclipse. Thank you all for your attention.